Welcome to APEC. It's April 9th, and I'm your moderator, Tim Ventura. I'd like to thank everyone for joining us on this call, along with everyone watching us on YouTube. So in today's session, Riccardo Storti will present on variable speed of light cosmology. John Brandenburg is going to be discussing GEM theory, and Ross Small is going to be demonstrating his RBI Machine propulsion device. We're also going to have Mark Sokol and Falcon Space provide detailed lab updates and the results of their latest experiments. And we're going to be finishing off the event with open discussion and at least one ad hoc presentation by conference attendees. So just a couple of quick reminders. You can view those conference replays, details, and speaker info on our website at www.altpropulsion.com. Please save your questions for the Q&A session after each presentation. You can raise your hand in Zoom using Option Y on Mac or Alt Y on Windows. You can also type those questions into chat, and we will go through those after each presenter finishes. Okay, so I want to introduce you now to our first guest. Riccardo Storti is going to be discussing variable speed of light physics and the implications that this offers for cosmology and reactionless propulsion. He's going to analyze a variety of important concepts in cosmology and discuss how our assumptions about the universe change in a VSOL model of physics. So let's welcome him to today's event. And now I will hand it over to him to get started.
Great, good stuff. Thanks for that, Tim. Appreciate it. Okay, good day, everybody. Look, I'm going to start. What you see now is a slide just that says high-level presentation. I've actually prepared two versions of what you're going to see. This is the high-level version, so the short version to try and fit into my slot here without too much effort. But however, if we do have time, I will go through a more detailed presentation. It's got a bit more information in it. All right, so let's start. So the title of my presentation is Cosmological Compliance Testing of Electromagnetic Propulsion Solutions. So what this whole thing is about is, in a nutshell, to start off with, and I'll come to this soon. The presentation's about putting forward evidence that I'll show you for the requirement for two tests, so a GR test and what I'm calling a dark energy horizon test. So that's what the presentation is about in a nutshell, and I'll kick into it now. So point number one there, Miguel Alcubierre provides a solution to faster than light propulsion within the boundaries of GR. So many of you know Miguel Alcubierre. He's got quite a name for himself these days because of the work that he did in the early 90s. I think it was, where he proposed the idea of if you contract the space-time in front of a craft and expand it behind the craft, and you kept everything inside that bubble obeying GR, then you could actually travel faster than light. Now, the Alcubierre solution has issues which have been widely discussed and debated for many years. However, our focus in today's presentation will be answering the question, is the speed of light of a warp bubble constrained by some kind of cosmological limit? And as I mentioned before, the answer that I believe is yes, and I've termed this the dark energy horizon. So the first result that comes out of the research is that a maximum permissible warp speed is 1.1 C. So yes, warp drive, warp speeds are possible, but not what you see in Star Trek. And the reason for that is because of what I'm calling the dark energy horizon. So the result coming out of this research is that all EMP solutions must be cosmologically compliant by passing two critical tests. So the first critical test I mentioned before is general relativity, and GR, I got to stress to people, is it works on the astronomical scale. So it's an astronomical scale compliant test, and it works very well on the astronomical scale. However, we also find that we need a second test, and that's what I'm calling the dark energy horizon test. And that works on the cosmological scale, and it's a cosmological scale compliance test. Now, why do we need to answer the question above? Well, it's because GR is only about 4 to 5% successful on a cosmological scale. So 95 to 96% of the physical universe was not predicted by GR, nor is it described adequately by GR, because it misses things like dark energy and dark matter. The example for that is that the cosmological constant within Einstein's equation was intended for a static universe, not for an accelerating universe driven by dark energy. And the cosmological constant, as stated by Einstein, is in fact, as the name suggests, a constant. There have been, you can find work suggesting that it's related to dark energy. No one knows for sure, but that's the primary candidate these days. And even so, the current belief, the standard model of cosmology belief, is that even dark energy is a constant input into that cosmological constant. Now, the Alcubierre solution is primarily reliant upon GR. Therefore, if GR is 95 to 96% incomplete, it follows that the Alcubierre solution is also 95 to 96% complete. Next slide. What does the solution look like? Well, look, lambda, which is the cosmological constant, and C are not constants. They have evolved over cosmological time, as described by what I call EGM. And I'll speak a bit more about that in just a moment. Now, at the moment, C is a definition, and that is really, really important for everybody to hang on to this. The speed of light the speed of light in a vacuum is a definition. It is not a measurement. It used to be a measurement, but it is no longer a measurement. It's a definition. And what I'm saying is that that is only valid at the cosmological event horizon. Everywhere else in the universe, it's in fact less than C relative to that definition. And the reason why it's C only at the cosmological event horizon is because it's the only place or boundary in the universe, is probably a better way to describe it, that actually, where space-time actually is flat. Everywhere else in the universe, space-time is curved. Even the addition of a single photon in the most deepest, darkest reaches of space somewhere, and you're a long way from everything else. You add one photon to it, you're curving space-time. So that's a really important point that I wanted to deliver to everybody quite forcefully. The cosmological event horizons should not be confused with the dark energy horizon. And that's what I'm proposing here. The dark energy field is a massive photonic field. That's what I claim it to be, and therefore can't expand at a rate of C. It expands at a rate of what I've labelled there H sub phi. The normal way to represent that would be H sub 0, so Hubble's constant, but the speed of light at the dark energy horizon, I'm saying, is 0.92 C. So it's not quite C, it's just below C, and it's just below C because the dark energy field is a massive photonic field. And if you read one of my publications on Hindawi, you'll see that I put forward a very persuasive argument for exactly that. Anyway, any physical measurement of C in the laboratory is merely an approximation of its defined value for a flat space-time manifold. So, as we all are aware of, experimental uncertainty, it's with us all the time and everywhere, and there is in fact no way that we can ever verify by experiment the defined value of C. So there's always that question mark hanging around. Now, if you look at that, that representation there, what you'll see are three circles. The black circle represents the expansion of the cosmological event horizon, and the speed of light at that boundary is the defined value. And we all know what that is. Now, the rate of expansion, h sub phi, is Hubble's constant. That's my calculation of Hubble's constant. And you'll see it's very close to the standard model of cosmology value. And I'll come back to that a bit later on because there's some important information around that. The red boundary is, red circle is the expansion of the dark energy horizon. And that's where I'm saying the speed of light is 0.92 C. And the blue region represents the expansion of the observable cosmological horizon. And the speed of light there, so for us, is 0.84 C. And the rate of expansion is 67. So the rate of expansion is constant across all of that naturally, as you might expect. Now, moving on. I should also point out that I've also labelled there between the red and the black boundary. That's flat space time, and the dark energy field is what I'm describing here as quasi-flat, and the blue region is curved space-time. And it's important that everybody consider, pardon me, that in GR, what we tend to do, and using black holes as an example, what we do with GR, and what we can only do with GR, is stand somewhere outside the black hole and look down. Whereas in cosmology, you're at the bottom of the gravity well and you're always looking up. So we need to make this important distinction, operational distinction between GR and cosmology. So I just wanted to point that out because it's something that I keep forgetting to pass on. Okay, here we've got a solution architecture representation. So at the bottom of the pyramid, you've got general relativity. On top of that, I'm a big fan of the polarizable vacuum model of gravity. And then on top of that, you've got zero-point field theory. Pardon me. To the side of that, you'll see along here electrogravity magnetics. Now, that's a methodology that's been developed by myself and Todd Desiato, and there's been significant success in that space in describing lots of things in particle physics around the mass and size of fundamental particles. We develop exact solutions for fundamental particles, notably the proton and the neutron, both of which have been experimentally verified to great precision. So it's pretty difficult to poke holes in that when it all lines up with experimental observation. And I've sort of taken that particle physics stuff the next step up using BPT. Now, BPT is Buckingham Pi theory, and applied that to cosmology. From that, I've then been able to do two things simultaneously: derive the time history of the cosmological constant, and also the time history of Padov's refractive index. From that, I can then get the variable speed of light, and made sure that when that all happened, that it lined up to the cosmological constant, and it does. And validated that against standard model of cosmology derived value of cosmological constant. So there's a bit of a pathway there, but as I'm hoping you'll see, it's been worth the effort. Okay, so I mentioned, pardon me, electrogravity magnetics. So that's the key really to all of our particle physics stuff and my cosmology stuff. And the question then comes is, can EGM be trusted? Well, yes. You know, I'm biased, but yes, and because now, point number one, it successfully derives 30% of the information listed in the particle data group 2021, and it's not just 2021, I mean, the 2021 results are the same for a number of years now, astrophysical constants and parameters, right? So, for example, the particle data group publish in 2021 published a Hubble constant value of 67.4, and I derived 67.1 something. You can see it on the previous slide. Now, just to emphasise that, I'll just put up on the screen here at the moment. So here we've got the astrophysical constants and parameters. This is 2019, but the results are the same as 2021. It's just that I happened to mark this one up in the 2019 when it came out. So what I've done here is I've highlighted all of the parameters that I'm actually able to derive to greater significance, greater precision than the particle data group. So my results align with all of their results, but I actually take it a little bit further. Now, as it works out, all those highlighted regions works out to about 30% of what's actually on this. So that's just the first indication that EGM can be trusted. It's not the last, it's just the first indication. Now, the second point here is EGM successfully derives experimentally verified solutions to particle physics challenges. Well, that's what I talked about before. There's a link there, and if you download, by the way, I made sure that, so if you guys people want to download the actual file, all those links should work. I went to great effort to make sure that it worked because I did have some problems. So anyway, if you click on these links, it'll take you to all of these documents. Now that's just point number two there. That published paper there. That's just one of a number of papers. It's not the be all and end all, but that does actually contain the exact solutions to the proton, neutron, and electron. And you'll see that the proton and the neutron align precisely with experimental observation to astonishing precision, I might add. Anyway, point number three, it predicted the value of the Hubble constant. So this is something else that I want to crow about. In 2008, I predicted the Hubble constant. It's published in the links there. That's one. It's published in a couple of places, but that's one. That's the. I attended a physics conference here in Australia in Adelaide in 2008. So that's that first bullet point. That's where that's from. So that's officially in the literature. Now, I predicted this result 5 years in advance of experimental confirmation by the 2013 Planck satellite. So in 2008, if you look at these other couple of links underneath that, in 2008, the Hubble constant was reported by the particle data group as being 73 kilometers per second per megaparsec. So when my value came out at 67.08, I thought, oh God, it doesn't look very impressive. But I thought, well, bugger it, that's my result, so I'm going to publish it, and that's it. And I attended the conference and published it. Then in 2013, the Particle Data Group, after the 2013 Planck satellite results came back, they published their result at 67.3. So it was a big jump by the Particle Data Group to go from 73 to 67.3. And the reason it was 73 is because 73, in those days, before the Planck results, the Hubble constant was experimentally determined by looking at celestial objects, supernovae and stuff like this. In 2013, with the Planck satellite, it looked at the whole universe in one go. So that's why in 2008 their result was 73. And in 2013, it dropped down to 67.3. So, look, I don't know whether any of you guys are much into cosmology or not. Not everybody is. I accept that, but that is no small achievement, I can assure you. Now, point number 4 is successfully derives experimentally verified solutions to cosmological challenges, and you can click on that link. And if you do, what you'll find is a paper that makes a prediction that I firmly believe is going to be verified by the James Webb Telescope, hopefully sooner rather than later. And that prediction is that the James Webb Telescope is going to observe and experimentally confirm that the universe is older than is currently believed. Now, the universe is currently believed to be 13.8 billion years old. I challenge that. I say it's in fact 14.57 billion years old, so 900 million years older than what it currently is. Now, obviously, when I say the James Webb Telescope is going to measure this, well, they're not going to measure it. I mean, no one's got a 14.57 or 13.8 billion year old clock that they can press the stopwatch on or turn it off. So the cosmological age is a calculation. It's not actually a direct physical measurement. But anyway, that's my prediction, and that goes against absolutely everybody and his dog. But I absolutely believe that that's going to be confirmed. All right, now the name of that paper that contains that is The Existence and Effect of Dark Energy Redshift on Cosmological Age. And you'll see in there, if you can be bothered or interested, how I calculate 67.118 kilometers per second per megaparsec. Now that's an improvement on my 2008 result. And the reason I'm able to do it, and the reason why standard cosmology can't, is because I'm able to constrain everything that I calculate to the cosmic microwave background radiation, and the standard model of cosmology cannot do that. And for that reason, everything that they do is an approximation. Anyway, look, back to the variable speed of light solution. So what I've got here is my temporal solution for the cosmological constant. You can see 2 regions there. You've got a primary solution and the supporting equation. Now, that's all an exact solution, right? So that's an exact solution for the cosmological history of the cosmological constant. So you can plug those into your spreadsheets when you've got time and play with them and do whatever you like. But that's it. That's the evidence, and that is bang on correct, and I'd stand by that. Now, how can I say that? Well, look, here's the first little bit of evidence, and this is not what I would consider most convincing. Maybe someone will, but this isn't bad. I'm actually able to calculate there the value of the cosmological constant today. Now it's 0.79, say, and the standard model of cosmology derived value is 1.09, say. right? Now, it's important to for me to emphasize here what I've got there in the blue text in the box. The PDG value of lambda is not a direct physical measurement. It's a derived value based upon the physical measurement of cosmic microwave background radiation. Now, being a derived value, it is only relevant subject to the underlying assumptions within the derivation. Now, this means that the tolerance value in particular only applies to the set assumptions, and that's really important, right? The most obvious assumption is that lambda is constant by mathematical definition, as stated in Einstein's equation. Now, I'll also point to the fact that the PDG does not specify lambda to have a subscript 0, which is typically associated with the present day or present epoch. Now, something I'll point out, I want to mention about these numbers. Now, if you can see my T equals T sub phi result, 0.79, that's the present day. That's the value that I say the cosmological constant is today on Sunday, the 10th of April. Now, underneath that, you'll see T equals 3/4 T sub phi. Now, that's when that 0.935 is the result when the universe was 3/4 of its current age. Now, you'll see that both of those results are very close to the SMOC derived result. And in fact, in the detailed presentation that you can skip forward to in your own time, you'll see I'm actually able to produce stuff very close to that, to that red one there, to the PDG result, very easily. It's trivial, right? I can do it very, very easily. However, what I want to point out is that with my primary solution here, the present day result, say call it 0.8, it's very, very close to 1, but the 0.935 result is in fact even closer to the SMOC result, to the standard model of cosmology result. And the reason why I've highlighted that is because the derivation of that 1.09 result in the standard model of cosmology, we've got to remember that the standard model of cosmology, for them, lambda is constant. It doesn't vary. It is constant. So what I claim they have done is they've looked up in the night sky, they've made their observations, done their calculations, and what they have actually found is the maximum. Now, that T equals 3/4 T sub phi result, that is the maximum, that's the local maximum since, I'm going to use a SMOC idea here. That's the maximum value of cosmological constant since the SMOC says cosmological acceleration began, right? That's why they get that result, right? So they get that result, they get their result for two reasons. One, they maintain it's constant, right? I dispute that. And two, when they look at the night sky, what they're actually calculating, although they don't realize it, is the maximum value since about 7.3 gigayears. And 7.3 gigayears is when the standard model of cosmology says the universe started accelerating, right? And they're wrong about that as well, in my view, right? So what I'm saying here is that I'm right, they're wrong, basically, right? Okay, I'll move on to the next one. All right, so here we've got actually a plot of the cosmological history of lambda. Now, I'll draw your attention to this first graph up here. Now, along the y-axis here is the cosmological constant, and along the bottom line here, or along the bottom axis here, it's just time, cosmological age, right? So just ignore these arguments here, right? That's just my MathCAD way of representing time and here cosmological constant. So don't worry about that, right? Just look at the diagram. Now here, you'll see that I've actually calculated when the Big Bang occurred, right? And that's at 3.6 by 10 to the minus 43 seconds, right? That's when the Big Bang occurred, right? So all of these are my results, right? They're all my results. So the Big Bang occurred here. The cosmological constant dropped down to 0. It crossed the axis, it's 0 at 5 by 10 to the minus 43 seconds. It then went negative to, now we'll jump over to this other graph here. It then went negative and stayed negative until a half of cosmological age. So it's 7.3 gigayears. So, and then at 7.3 gigayears, it was 0, lambda was 0, and then became positive after that. Now, this is actually really important, but I'll move through these results here. All right, so point number 1, Big Bang occurred, then. It had a value of 1.25 by 10 to the 64. It was 0 at that time index. It was 0 again at that time index. And you've got to remember, I call it a half T sub phi. You've got to remember that's T sub 5, that's cosmological age. That's my cosmological age, right? It's 14.57 gigayears, which is the Hubble age, right? Standard model of cosmology says, no, it's 13.8, right? So a half of my value equals 7.28. That's really important. Please remember that. Burn it into your brain, because I'll come back to that a bit later on. Lambda maximum occurs here, right? And that actually occurred at 10.9 gigayears. And it had a maximum value. That's what you saw on your screen before. So that's the maximum value over here. That's when lambda equals 0 here, the second instance. And the present epoch is 14.57 gigayears, and its true current value on claiming is that. Okay. Now, is there any experimental evidence validating our solution? Look, good question. I'm glad you asked. And the answer is yes, because Fermilab assert that the universe began accelerating, and that's when Q equals 0, right? At approximately, now Q being the deceleration parameter, at approximately 10 gigayears. Now you can find it in this link here. You can go to page 44, and it's, I don't know, it's a few lines in. It's easy to find, right? Okay. Now we calculate that the deceleration parameter equals 0 at 9.6 gigayears. Now I should also say that not only have we calculated the cosmological constant, but also all of the standard model of cosmology's important parameters. So the dark energy density parameter, and sorry, I'm talking about also the time history of all of these things, right? So the dark energy density parameter, the matter parameter, and the deceleration parameter. So we've got time histories for all of these things, and they all line up with the cosmological constant, the values and the graphs and the behaviour that you're seeing now, right? Now, so keep in mind that Fermilab say that the deceleration parameter was 0 at about 10 gigayears. We calculate precisely 9.6 gigayears. So our calculation lines up exactly with Fermilab. So that's the first point, important point, good point. Here, the particle data group assert that Q equals 0. So they assert that the universe started accelerating. And it's, in fact, if you look at the particle data group sheet that I showed up before, it actually says that this is when the universe starts accelerating, right? Now, they say it starts accelerating at 7.7 gigayears, right? However, we show that the PDG 2021 Q equals 0 result is in conflict with Fermilab, right? So these two things are actually in conflict. They don't agree with each other. The correct interpretation of their result, that's of the PDG result, is that lambda equals 0, right? Now, we calculate that age as being 7.3 gig years. That lines up just far too closely, far too neatly, far too nicely with the PDG result for it to be ignored, right? Now, the standard model of cosmology, by the way, does not, they are unable to calculate. I should stress this because I just assume that you guys know what I know, and maybe some of you do, maybe some of you don't. So I may just tend to glance over things, but I should also stress that the standard model of cosmology cannot determine, they cannot calculate when Q equals 0, right? They cannot say it happened at this time. No, I can do that. They can't do that, right? So I just want to emphasize that. All right, now moving on to the next one. All right, so the cosmological history of C. Now this is you know, this is the money shot. This is what everybody's been wanting to hear about. All right, so once again, I'll just explain the graphs and I'll then move through these points. Okay, so here we have the Big Bang occurred. That's the time where it occurred. So it's the same as what's on the other graph. The reason why I have here the Big Bang occurring exactly at this axis is because in MathCAD, I couldn't put more than 2 vertical time markers here. So I had to set that one, I had to set the boundary there. So just want to explain a bit of the difference why between this one and the other one in terms of formatting. Okay, so the y-axis here is speed of light operator. So what that means is I've basically just to make it easy, because you know the numbers can be very, very large or very, very small, and having the units hang on the end of it just makes it that much more cumbersome. I've removed the units so that when you see, for example, C equals 1, what that means is that C equals C. So C equals the speed of light. Right? If you see C equals, if you see it a half, right, then C equals half the speed of light, right? Okay. So the vertical axis here is the speed of light operator. And the horizontal axis is just cosmological time, cosmological age. I've got 2 lines here. I've got the red line, which is it's the EGM dark energy solo. So speed of light operator equals solo. Okay. Now the red one is so both of them are derived from the EGM construct, and that's why I say I make it clear EGM in the labeling. But I also do that because I can very easily flip between the standard model of cosmology's representation of anything and the EGM representation, right? So for me, it's very easy to just flip between the two. And that's why I have to make that distinction, because I do that quite a bit in my solution algorithms. Anyway, so here at the instance when the cosmological constant equals 0, what we see is that the speed of light equals C at only that instant for the dark energy solo. So the blue line is the cosmological solo, so speed of light operator. And the difference between them is this: dark energy is explicitly dark energy and only dark energy. The cosmological operator, the cosmological solo, includes dark energy and matter and everything else, right? Includes everything, cosmological, as the name implies. And the reason why it's important to point that out is because the cosmological line also includes the contribution of dark energy, because dark energy is, well, dark energy and dark matter, it's 95%, not to 96% of all the mass of the universe, right? So I just wanted to point those two out. The blue line is the everything solution. The red line is the dark energy solution, solo only. Okay, now at T6 there, I'm not sure if I included T6 somewhere here. Maybe I didn't include it. But anyway, at T6, and if anybody's interested, I can give you the exact time for that. That's when the blue line crossed the c equals 1. So the speed of light equals the speed of light, you know, boundary there. Now on the right hand side here, we've got okay, so firstly on the graph here on the left hand side, that goes up to 10 to the minus 42 seconds, I think, right? So the first 10 to the minus 42 seconds appears here on the left-hand side. On the right-hand side, top right-hand corner, we've got up to 10 to the minus 3.5 by 10 to the minus 22 seconds. So as you can see here, what happens is that actually rises up very, very fast. Now that's cosmological inflation. So cosmological inflation occurred from 0 up to this boundary here, right? And I've got the actual time, the actual instant in time when cosmological inflation stopped is that 7.78 by 10 to the minus 23 seconds. Now at that point, at that instant, the speed of light was 10 to the 38 times greater than it is today. Right, and it's only instantaneous, and it starts decreasing from that moment on, right? But I wanted to highlight that. Now, what that does suggest is that because it existed naturally in the past, that if you can somehow study whatever the conditions are, whatever the conditions are at that instant in time, then in theory, if you could reproduce those conditions, you would be able to get much greater warp drive speeds than the 1.1 C I'm claiming is available to us today. All right. Anyway, you can see the numbers there. You can read them for yourself. It's pretty straightforward. Down the bottom right-hand corner here, we have the second half of the cosmological experience. So at this point here, at a half cosmological age, again, C equals 1 in the dark energy field and lambda equals 0 at 7.3 gigayears. So the standard model of cosmology, the PDG, they say that 7.3 is 7.7 plus or minus, a tolerance of 0 point something, or I can't remember, but you can have a look at that yourself, right? So again, that all lines up. So this number here lines up with the standard model of cosmology. This makes sense, at least to me, and this lines up with that. So I'll just cover off the points here. Now, utilising the polarizable vacuum model of gravity and our primary solution, so that's the equation you saw on your screens before, for lambda, we're able to plot the cosmological history, right? Now, the speed of light in the dark energy field is I'll call it 5%, right? So 9.5% higher than the speed of light in the baryonic field. Now, the baryonic field being, you, me, us, all the matter in the universe, right? But in actuality, right, that also includes, dark matter as well, right? So anything that isn't dark energy, I've just, for brevity, labeled that the baryonic field, because that's what most of it is, right? Anyway, so the dark energy field is 9.5% higher. So the speed of light in the dark energy field is 9.5% higher than the speed of light in the everything else field, right? Now, what that implies, and I cover off this in the points later on, is that during at the instant of the Big Bang, the dark energy field actually started its journey slightly, just a moment in time, before the baryonic field. So what's preceding us as our universe expands is a dark energy field, and we're moving along with everything else. This is what the dark energy field actually slightly precedes us. Okay, now, as I mentioned before, during cosmological inflation, the speed of light reached 10 to 38 orders of magnitude greater than today. The solo has equaled 1 twice in our cosmological history. So only twice in our cosmological history has the speed of light actually been c. Every other time it's been different. And the dark energy field solo, I'm calling that quasi-flat space-time, for the present epoch is 0.92 c. So because this is a solo number, it's just 0.92, but it actually means 0.92 c. And consistent with the diagram you saw before, in our cosmological observation, it's 0.84 c. All right. So all right, I'll move on. And yeah, just down here, you can see where the present epoch is over here. And here you can see, I'll just, maybe you can't see that very well, but that's actually 4.6 gigayears. So in the cosmological solo, C equals C at a cosmological age of 4.6 gigayears. Okay. Now, what's the lesson learned out of it? Out of this. Now, point number 1, traveling faster than the local value of c is physically limited by the rate at which the universe's space-time fabric is expanding. And that's the number that I've calculated there, right? Consistent with all experimental observation, right? If this were not the case, one could theoretically leave our universe after achieving escape velocity, right? And this might introduce a paradox. So here's a calculation for the escape velocity, nothing new. You know, it's a few hundred years old. The actual calculations, I've just plugged in my numbers, right? So it's just 2gm on r, square root of 2gm on r, and I've just plugged in my numbers. So I've plugged in my calculation of cosmological mass, again, in agreement with the standard model of cosmology. I've plugged in my value of Hubble radius, length, and once again, that Hubble length is in agreement with the particle data group. If you look at their results, you'll see that my result is just it's bang on, right? Or rather, theirs is accurate compared to mine. That's the way I like to view it. Now, pi r, the observational radius or distance, again in agreement with the standard model of cosmology, and the observable universe, again that calculation is in agreement with the standard model of cosmology. You might see it listed or referred to as 92 billion, or maybe even 90 billion. Yeah, 92 billion light years or 93 billion light years, etc. But it's basically the same, and that's how you get it. Very, very simple, right? It's just basic circle stuff. The escape velocity. So what I actually calculate is that the escape velocity for our universe is the defined value of c. So it is exactly 2.999 by 10 to the 8. Right, so that, at least in my imagination, lines up well with what I might think. Being able to escape the universe would be a bit problematic, because that would then imply that mass and energy aren't conserved. Now, the speed at which baryonic matter travel, assuming GR constraints are also satisfied, is limited to the speed of light at the dark energy horizon. So if you remember what I had on screen before, our limit at the bottom of the gravity well looking up, our baryonic limit is 0.84 c. Sorry, that's what the value of c is for us right now, right? But the farthest that we can go is up to 0.92 C, but that's relative to the defined value, which is at the cosmological event horizon. To us, we measure C, right? So to us, it looks like C. It looks like C everywhere, right? But that's because our rules and clocks shrink. Okay, so lessons learned continue. Point number 2, GR is only 4 to 5% successful on a cosmological scale. 95 to 96% of the physical universe, when you include dark energy and matter, was not predicted, nor is it described by Einstein's equations. So simply put, and this is important, agreeing with GR is simply not enough, right? Point number 1 there, 2.1, consequently, it follows that a propulsion solution which satisfies GR only is insufficiently rigorous to be deemed cosmologically compliant. So saying that you've got a solution and it obeys GR, well, that's good. It's good, it's good, but it's not enough, right? Now, GR works well on an astronomical scale, but it does fail spectacularly on a cosmological scale. And I've wondered for a long time why I keep hearing statements about GR, it's very well tested. Well, it's not. It really, really isn't. And it's important that I touch on this as well. It's not. As an engineer, what's well tested are thermodynamics, the laws of electromagnetism. These are well tested. GR is barely tested. Anyway, that's just a debate for another day. So anyway, GR works very well, fantastically on the astronomical scale, but it does not work well at all on the cosmological scale. And the reason for that is the cosmological constant. And that's why I've spent so much time covering the cosmological constant here, is because we've got a fix for it. So when you plug our cosmological fix for the cosmological constant into Einstein's equation, that then fixes Einstein's equation so that it does describe on a cosmological scale things very well, and it works then on a cosmological scale and describes everything on a cosmological scale. But unless you do that, if you stick with what he's got, all right, with what Einstein put in there, it only works astronomically, where the cosmological constant doesn't really matter very much. Now, 2.2, all solutions for electromagnetic propulsion must be shown to be cosmologically compliant, as well as being GR compliant. So this is a critical requirement which cannot be avoided. So not only do you have to satisfy GR, you've also got to satisfy the dark energy horizon test. Now, cosmological compliance requires that the limit of the expected value of the electromagnetic propulsion apparatus, so its velocity, cannot exceed 9.5% of the local value of C. So that means that the fastest that you can go, the fastest that you can build your warp drive machine to go is 1.1 C. Look, that is, if you could do that, that's enormous, right? That is just a massive achievement, right? Not to throw any water on that. It's a massive achievement. What I'm just trying to communicate is that these Star Trek velocities, warp 10 and the rest of it, and warp 13, I think in one episode, it's not real. It's not physical. It's not even theoretically possible. Point number 4 there, the cosmological compliance condition is set by the speed of light at the dark energy horizon. And that's what I've been saying all along. And that this implies that the cosmological expansion of dark energy precedes cosmological expansion of baryonic matter, just by a fraction. Therefore, point number 5, breakthrough technologies at 1.1 C may not represent a practical means of interstellar locomotion, with the possible exception of our closest stellar neighbours. Summary, key takeaways. Point number 1, axioms of the PV model of general relativity. Right? Now, the definition of C is only a valid limit at the leading edge of our expanding universe, where the fabric of space-time, the fabric of the space-time manifold is perfectly flat. Right? So there's no energy there. It literally is nothingness. That's the only time that the speed of light, its definition, is actually applicable. Everywhere else it's not. Now, where was I? Now, this is often termed the cosmological event horizon. So everywhere else in the universe, the space-time manifold is curved due to the presence of various forms of stored or transient energy. And that's what I was talking about before. As soon as you plop just one photon into a totally flat region of space, you've curved it, because there's energy there. You've added, you've curved it. Now, B, and this is really important, right? Now, the illusion of measuring C locally is maintained because our rules and clocks scale with local space-time curvature. So the reason why we always measure C as C, because this is something that people like to say, well, it's difficult to get people to understand, and Todd might agree with me on this, Todd Desiato might agree with me on this, that it's difficult for people to get people to understand that our rules and clocks, so what we use to measure C, are sitting in the same gravity well as what we're measuring. So everything has shrunk, has scaled, right, accordingly. So that's why we measure C as C. And I think I've presented some, I hope, persuasive evidence, experimentally verified evidence, as to why the idea of C not actually being C anywhere other than the defined, around the cosmological event horizon. Hopefully that's persuaded some people anyway. So point number 2 there, experimental uncertainty precludes the possibility of exact confirmation of its defined value. So consequently, we necessarily assume that approximate equals exact, right? So we're never going to be able to actually confirm exactly that what we observe in the laboratory is the defined value of C. Point number 2, when applicable, all calculations should be constrained by the cosmic microwave background radiation. That's T sub naught. So what I'm talking about there is utilising, for example, the values of omega, Hubble constant, and cosmological time. So omega being dark energy density parameter, Hubble constant, cosmological time. The ones that I use, right, the ones that I've developed, which are constrained to this value here, rather than using the standard model of cosmology values, which are not constrained. And that's actually a significant area that the standard model of cosmology falls over. All of these values here are independent conclusions, and they're not constrained to T naught, which is very, very accurate. Anyway, you can read about that there if you want to, just follow the link. So point number 3, any viable EMP solution must satisfy the requirements of general relativity. So that is what I'm calling the first critical test. Moving on. Point number 4, the phenomenon of accelerated cosmological expansion is not explicitly addressed in Einstein's solution. I've talked about that ad nauseum. Consequently, at least one additional test is required when talking about when considering accelerated cosmological expansion, because Einstein's solution does not consider that. However, the reality is we live in an accelerating universe. So that's why Einstein's GR does not work on a cosmological scale, because it excludes that component. Now, the name given to this contribution is dark energy. That's typically what people are attributing the effects of dark energy 2 is the 0-point field. So out of this, we get the second critical test, which I'm calling a dark energy horizon test. And this test involves calculating the EMP's solution, its local value of C. If the calculated value of C exceeds the expected value, or the expected value being the defined value, by the way, greater than 9.5%, right? So if once you run your numbers in your, in your design process or your investigation process, you run your numbers, and if you get a value of 2C, 3C, you expect your apparatus to be able to go, then you've got an issue. The most that you can go is 9.5%. If you're over this number here, then what you've come up with is not cosmologically compliant. It violates cosmology. Now, point number 3 there, therefore, the maximum local value of warp drop cannot exceed 1.1C, and I've repeated that number of times. Now, if point number 5, if the cosmological event horizon is expanding at an experimentally observed rate of Hubble's constant, it follows that to avoid some kind of paradox, there must be a physical limitation to how fast you can go. Now, if someone comes up with a solution of 200C, right, what that means then, if you think about it, right, what that means then is that if you travel far enough, at 200C, you can leave the universe, right? Its escape velocity, I'm saying, is 1C, right? And that's very very mainstream conclusion, that, right? The escape velocity is C. All I've done is plug in my values. So that would violate the laws of being able to do that, would violate the laws of conservation of mass and energy, right? So the universe would be able to get fatter or get skinnier if objects were able to leave. So that would just break physics, right? And I just can't accept it as true. Finally, there, in addition, we've shown that the escape velocity for our universe is the defined value of C, right? So look, that's it, viewers. That's the end of the high-level presentation. There are a couple of things in the detailed presentation which I can go over, which aren't included, which relates to Todd Desiato's radiative damping model. I did mean to include that, right? But feedback I got was that my presentation was just too long and could be complicated for viewers, so I chopped some of it out. And there's also some really groovy graphs and predictions that I make. Well, look, one prediction I will make just very, very quickly, right? And because I want this on the record. So I'll go to this graph here, and here's my prediction. So on the right hand side here is the standard model of cosmology. These are all the figures that I've derived, right? So all these results I've actually derived, right? So I've derived everything that's expected in the standard model of cosmology, right? On the left-hand side is I'm taking it one step further. I'm saying that actual dark energy composition is only 50%. It's not 67%. I can derive that 67% easy done, right? But what I'm saying is that 67% is in fact wrong. It's actually 50%, and that 17% is actually being misidentified, right? Because a bit of thought of experiment supporting that is that it's misidentified because if we're looking out into space and there are no stars in front of us, we've picked a little point in sky, there are no stars in front of us, and we look and we look and we look and we look, we keep looking, we see nothing, then we conclude that it's dark energy that's that's driving things along, whereas there might in fact be a bit of dark matter there that we can't see, right? That's in our field of view. Anyway, so that's my prediction, and I'll explain on the record because I hope it's going to come true with James Webb Telescope. And there's also, look, while I'm here, there's also just a lot of other graphs, cosmological stuff. Anyway, so I had to jump over some stuff that that actually demonstrated that Todd Desiato's radiative damping model is actually cosmologically compliant and lines up very well with what I just presented. Anyway, look, so that's it for me. You know, for now, I'm done. If anybody wants to reach out to me, you know, they can, and I'm happy to, you know, assist any way that I can. So that's it. That's it, Tim. We can move on. Yeah, he's not there. All right. Well, I'll keep you guys entertained then. Look, I'll just I will go through a little bit of detailed stuff here until Tim comes back. What I want to jump to and highlight is, okay, a couple of things. So here, I actually, something that you saw before, I've got primary solution. I've also got secondary and tertiary solutions. So these are more SMOC, with more of a SMOC flavour, standard model cosmology flavour. You know, I can derive that. It's trivial. I've done that there, right? Now, if you look at the results here, as I mentioned before, I can get, you know, multiple instances of, you know, the PDG result here. I can produce. It's easy for me, right? I can produce it very, very easily, right? But what I've done is I've actually discarded the secondary and tertiary solutions because they are not, and the reason for that is because they are not constrained. Because for the secondary and tertiary solutions, I'm plugging in, right? I'm not plugging in. These solutions use data supporting SMOC data that is not constrained by cosmological microwave background radiation. So for that reason, I can discard the secondary and tertiary solutions because they're just too rough. So as far as I'm concerned, anything standard model of cosmology, it's rough, right? It's a rough calculation as far as I'm concerned. It's not what I would call accurate. So anyway, I can produce their results, you know, with very, very easily and to great precision if I, you know, wish to do so. But I had to try and chop some stuff out, so that's what I chopped out. Okay, so and here's a point that I'm making in the one of the detailed slides. But there are 3 flies in the ointment. These are not constrained by the CMBR, right? They're standard model of cosmology. This is standard model of cosmology stuff. It's not constrained by CMBR. Yeah, my stuff is, so I trust my stuff more than standard model cosmology. Okay, so I'll move to, okay, so here I'll cover off stuff that I wanted to talk about, I took out. I'm only going through this way, waiting for Tim here. So I've actually had a look at, oh, Tim, you're back.
Yeah, sorry, I know, I never left. Yeah, no, I've been here the whole time, sir.
Oh, because I said to you that I was finished.
Oh yeah. No, I didn't want to interrupt because you jumped right into the.
Oh, sorry, mate.
So, oh no, that's okay. Well, yeah, I would say just keep going and running through it. Yeah. Right. Yeah. No, I heard you. You're like, okay, well, I'm finished. And I was like, okay, I'm ready. And then you jumped right into a description of Todd's work and and some of the details. Right, okay. So yeah, I would say go for it, sir.
All right. Well, look, I'll just cover this off then. So I just want to shine a light on Todd's stuff because it's pretty good. So Todd's come up with a radiative damping model, and I'll leave it up to you guys to engage Todd and read about it, etc. But basically, what I do here is I show that Todd's zeta function. Well, this isn't exactly Todd's zeta value, right? So this is what I'm calling the dark energy damping factor. So Todd deals with the global value of zeta. I deal with it with its influence in the dark energy field. So I call it the dark energy damping factor because that's something I'm actually able to do. I'm actually able to separate out, for example, Puthoff's refractive index to the baryonic field, the dark matter component, the dark energy component. I can really break it down. lump it all together. Anyway, I just want to highlight that Todd's radiative damping model, his zeta function lines up absolutely beautifully with this. Every time the cosmological constant is 0 and the speed of light equals the speed of light, his zeta value is 0 as well. And it lined up really, really well. So that's why I wanted to speak about it. And it's important for a number of other reasons as well. But anyway, look, here's a couple. Here are exact solutions that I've prepared for the dark energy damping factor for the present epoch for today. So you can see those exact solutions. Where I can, I try and do exact solutions rather than numerical solutions. I always do numerical solutions, but anyway, here's the exact solution for the present epoch. You've seen that graph before. I spoke about that. Right, yeah. Now here's something that important as well. So lessons learned. So Todd's, so again, I'm referring to Todd's radiative damping model, right? Now, I believe it's an important quantity requiring further research because I'm able to show that the end of the cosmological reionization epoch coincides with when zeta equals 1. And that's at approximately 1 gigayear, right? And the temperature of the universe at that time was 11.8. Kelvin. So these are the values that I've calculated, right? But it's important to emphasize that the SMOC, the Standard Model of Cosmology estimate for the end of reionization is 1 gigayear, and that the temperature they say is 19 Kelvin, about 19 Kelvin. So my calculated results line up with the Standard Model of Cosmology expectation precisely. Here we have an exact value for the an exact solution for the asymptotic value of the dark energy damping factor. The next thing I sort of jumped over is my reference literature. So if you download the file, you can click on these. These all work. Sorry for the very small lettering, but I had to shrink it down to a small enough font size so that it wouldn't break the links. But anyway, you can download full calculations for everything here in the solution algorithms. Look, they're not easy reads, right? They're not easy reads, but look, I'm here. If anybody reaches out, I'll explain it to you. But anyway, that's just basically the algorithm that it's all done in MathCAD, and it's all there, and people can pull it apart and verify all of my claims, etc. So what else have I got here? Right, yeah. Now here are the graphs. I point out these graphs. Look, I explain the entire history of the cosmos in these graphs. All of the equations, everything anybody needs to verify for themselves is there, right? So I cover everything. Cosmological inflation process, everything. By the way, I should emphasize that the EGM construct organically derives cosmological inflation. It is not a band-aid that I had to put on, right? It just dropped out, and I was mortified. I was shocked when I saw this for the first time. So that's something else that I want to point out. Yeah, here we go, cosmological constant. Here's all the omega and you know, deceleration parameter and matter density parameter, etc. So these are all on the graphs. Lots of tables, exact, you know, very precise numbers there. So yeah, basically that's it. So look, just on this final diagram here, you'll see a way of representing, a good way of representing cosmology numbers or my cosmology numbers. Just draw a circle, give it the radius of the Hubble length, 14.57 gigalight years. Then everything on that surface, right, the perimeter of that circle is our universe, and it's observable. And those values line up with the numbers. So very simple trigonometry there. All right, Tim, I really am done now. I'm spent, I'm exhausted.
Okay, well, so let me do this then. Before we do anything else, Riccardo, let me see. I'm going to stop your screen share. I should apologize for the confusion. Yeah, I've been here the whole time. I've just been sitting listening to your presentation. So,
yeah, sorry, dude.
Oh no, that's okay. I think it was really valuable to go through all that material. So let's do this. I want to put this thing on gallery view, and everyone, please give a giant applause to Mr. Riccardo Storti. Riccardo, thank you so much. Thank you so much for coming back and presenting this. When you sent this to me, I got really excited about it. I was like, yes, this is awesome. This is, because I think it's really important to look at the fundamentals of those models, right? And if we change those models slightly, that opens up all these new worlds of possibilities. So thank you for coming back.